ready to start? Okay, great. So we're pleased to have Annamaria Ortu give the second talk of the workshop, and she'll tell us about constant scalar curvature metrics and semi-stable vector bundles.
Thank you for inviting me. And I'm going to talk about this project which is joined with Lars Martin's afternoon. And let's start with E over B via holomorphic vector bundle. Can you read, or should I write larger?
That's good.
So the Hitchin-Kobayashi correspondence of Donaldson-Uhlenbeck-Yau says that the slope stability, or slope polystability of E is equivalent to the existence of a Hermite-Einstein connection. So Hermite-Einstein metric on E. And on the other hand, so this is the first equivalence between algebraic geometric condition and solution to a geometric PD. And on a polarized, so on a smooth, well, I will be working with smooth projective variety X L, where L is an ample line bundle. The Yau-Tian-Donaldson conjecture predicts the equivalence between K stability and the existence of constant scalar curvature metrics. So K stability with respect to the polarization L and constant scalar curvature metrics in the first rank class of L. So I'm going to write CSCK for the constant scalar curvature Kaehler metric from now on. So let's now consider the projectivization of the vector bundle E over the base B, and let L over B be an ample line bundle. Then we can, so the projectivization meaning that P of the fiber over point is the projective space of the vector space over that point, and I represent this by pi. Then we can consider the tautological bundle OP minus 1 over P of E, which I would denote by X. And so its dual X is a relatively ample line bundle. Which, by this I mean that its restriction to each fiber is ample. And every time I say relatively, I mean something that holds when restricted to the fibers of this fibrations. So the goal is to relate the stability of the vector bundle E to the K-stability and to the existence of constant scalar curvature matrix on P of E, so on the projectivization on the total space of this fibers, with respect to K-stability with respect to or existence of CK matrix in the class given by C1 of H plus a large multiple of C1 of the base polarization, where by this I really mean the pullback of L of the line bundle on the base to X, and for each K sufficiently large. Okay, so more precisely, if given H Hermitian metric on E, then H induces Hermitian metric on H, on capital H, such that the first shell class of H is represented by the curvature of this metric, of the term connection associated to this metric, and this form omega restricted to the fiber of X is a Fubini-Studi metric. Okay, so we say that, so recall that H is Hermite-Einstein if the contraction with the base metric of the curvature of H is a constant multiple of the identity on E, where lambda is the Einstein constant given by C1 of E, times C1 of L to the n minus 1 over C1 to the n times n maybe, and yes, Einstein constant. So going back to our goal, if E is stable, so it's slope stable, meaning that it admits an Hermite-Einstein matrix, then this is a classical. It is a classical result. Of Hong that the following happens. So assume that E is a simple vector bundle, meaning that H0 of endomorphisms of E is just one-dimensional, which is minimal. And assume that the base B admits a constant scalar curvature metric omega B in C1 of L, and that the automorphisms of B that lead to L is discrete. And assume that H is Hermite-Einstein on E. Then P of E admits a CSCK metric in the class C1 of H plus K times C1 of L for each K sufficiently large. So this is this class. It's called an adiabatic class. And the idea is that when K goes to infinity, so when K grows, the curvature is concentrated in the fiber. And the base tends to become flat. And so first remark, and the second remark is that the Hermite-Einstein condition chooses the right Fubini-Studi metric. On the fibers. And so this is a classical result that deals with when E is a stable vector bundle. And so what I'm going to present today is what happens when E is a slope-semistable vector bundle. And okay, so maybe just for fixing the notation, recall that the slope of E is, I will denote it by mu of E, is given by the degree of E over the rank of E, and this depends on L, so on the uncoline bundles on the base. And we say that E is slope semistable or slope stable if the slope of F is less or equal, or equal equivalent in the semistable case to the slope of E for every subsheaf of F of E. And we say that it's slope polystable if we can write E as the sum of F1 times F, I don't know, L for where Fi are stable of the same slope. And so, so our main result can be, I will say it a more general version and then I will explain more precisely. But so assume that E is semi-stable, so slope semi-stable, and simple. Assume the same condition on the base as above, so B has CFCK metric, and the automorphisms of B, L are discrete. And assume that phi of E is K-stable with respect to H plus K L for all K. Then P of E admits CSCK metric in each of these class. So actually this is a more general version, but what we are able to do is to relax the K-stability assumption to only check in on certain test configurations. So we introduce what we call adiabatic slope stability. Of E as K-stability with respect to certain test configurations. That I will now describe. So if you take S to be a subbundle of E, then E degenerates to S plus E over S, as we can obtain from this subbundle of a short exact sequence, writing E as an extension S and E over S. And so in particular, this means that if we consider del var E to be the holomorphic operator on E, and let me denote this as E naught, so del var naught is the holomorphic operator of it. Then we can write del var E as del var naught plus gamma, where gamma is an element in omega 01 with values in the endomorphisms of E. So it's a deformation of the holomorphic structure. And so in particular, we can form a family E over B times C that detects this degeneration. So ET is isomorphic to E over B for all T different from 0, and E0 is E naught. Okay, and so the projectivization of it of P of this family over B times C is a test configuration for P of B. If you project further onto C. And yes, with central fiber P of E0. And ample line bundle given again by HK equals H plus KL, where L is again pulled back from B. And H is the O1 bundle on P of E. And so this test configuration depends on S, of course. It depends on the subbundle. So let me denote it by X S. Okay. So now if we so if we can compute the Donaldson-Futak invariant of this. And this was done, well, in Ross Thomas, for example. They computed the Donaldson-Futak invariant of the deformation to the normal cone, which is essentially this test configuration when one has contracted an exceptional divisor in the central fiber. But we also did it using Legendre's localization formula of the Futak invariant. So what is this Donaldson-Futak invariant? So of this XS with respect to HK, we can expand it in K in powers of K, and we obtain that the leading order term is K to the n minus 1, where n is the dimension of the base, times some constant times the difference of the slopes. So the slope of E minus the slope of S. And then there are some lower order terms.
So XS, you've written it's a submanifold of PV, or I guess it's equal
no,
to
sorry. Yeah, this was equal. So it's I will denote it like this. It's just to remember that it depends on which subbundle you choose. Thank you. And okay, so essentially you see from this formula that if E is slope stable, then Donaldson-Futak invariant is positive with respect to this test configuration. If E is unstable, then it is negative, so there's no way of having constant scalar curvature matrix on the total space. But if E is only semi-stable, then the leading order term is 0. So yeah, if E is semi-stable and S is the stabilizing subbundle, so it's such that the slope of S is equal to the slope of P, then the Donaldson-Futak invariant is of order n-2. So it might be positive. It might still be positive after the leading order term is 0. And so we define, we say that E is adiabatically slope stable if the Donaldson-Futak invariant of these test configurations obtained using a subbundle S is positive for each subbundle. And so, actually,
you only need to consider subbundle or subsheet.
Yeah, only subbundles. Yes. So here was a red choke. So here I can replace this with this adiabatically slope stable. Okay. So okay, I will maybe I can use only the one on the top. I will explain a bit how to prove, so how the proof goes. So the first step, of course, is setting up the program. So set up. Yeah.
So do you mean that adiabatical slope stability implies K-stability, or you only need to assume this adiabatic slope stability to prove this?
Yes, yes. I only need to assume. So, of course, K-stability implies adiabatically slope stability. Yeah. And from our result, the opposite is true, but only going through the existence of CSCK matrix. But yeah, by this I mean that I can replace the assumption that it's K-stable with the assumption that it's adiabatically slope stable. So it's K-stable only. We need only to check on these test configurations that arise from subbundles, essentially.
To prove the existence of CSCK.
To reduce CSCK matrix on the data space,
so
yes.
You don't mean adiabatic slope stability implies K-stability?
Yeah, at the end, yes, because the existence of a CSCK matrix then implies K-stability from the Gaussian non-conjectural part. Okay, so
but here you mean K-stability is K-polystability.
yeah, I mean the Donaldson-Futak invariant is positive on these test configurations.
If it is not product.
If it's not a product, yes, yes. Yes. Okay, so if E is a slope semi-stable, then we can consider the Jordan-Alder filtration. Well, a Jordan-Alder filtration, E0 S1, SD equal E, from which, so such that the slopes of Si is equal to the slope of E. And from this we can produce the graded object of E to D of the quotient, which is polystable. And also here we need to assume, so another assumption that I didn't write before, but we need to make it here that the graded object is a vector bundle, which is to say that E is sufficiently smooth. And so, similar to before, E, the vector bundle E degenerates to the graded object, so to its graded object, which means that so with a deformation as before, and so we can describe the deformations of the graded object of E with as, so maybe it's better to say that we can parameterize them. The deformations of the graded object with a subspace of H1 of B and E. And so, in particular, there exists a map from an open subset here inside the space, which I denote JE of holomorphic, so del bar operators on E. So maybe it's important to specify that.
Just the boards bit.
Sorry. The E and the graded object of E are isomorphic as smooth vector bundles. And so we can consider the space of all del bar operators and so holomorphic structures on E, so in such a way that the origin of this open ball around the origin is mapped to the del bar operator of the graded object, and there is some point xe that is mapped to the del bar operator of E. And this map is equivariant with respect to the action of the group G of automorphisms of the graded object. And okay, should go on the other side. And so, passing to the projective bundles, we can describe, so we can compose this map phi from B to JE to the space of complex structures on the projectivization, since the del bar operator induces a complex structure in the projectivization that are compatible with the projection to the base. And so in this way we can describe the deformations of P, of the projectivization of E to the projectivization of the graded object. And so the goal is to construct So to find constant scalar curvature metric, so scalar curvature of omega plus k times omega b, j on E. So here we have xe maps to the bar operator of E, maps to the complex structure on the projectivization. And we want, so maybe I can write this as a j of x e. I want this to be constant, so to find the zero of this operator, and then where as omega, so as the relative Kaehler form, which was is induced, the one induced by the Hermite-Einstein structure, so Hermite-Einstein metric on the graded object. And so the key here is to use the equivariance of this map phi to phrase this equation, so the constant scalar curvature equation, as a moment map equation. On V, so on this space of deformations. And to do this, we use the machinery developed by Darvan and Hallam, which is can be described as follows. So we can view the deformations of the graded object as a universal family over V, which as smooth manifold is V times the underlying smooth manifold of P of E. So is the underlying smooth manifold of P of E, which is the same as, so it's isomorphic, smoothly isomorphic to the one induced by the graded object. And so the action of G, well, G is a reductive group, so it's a complexification of K, where K is the group of unitary automorphisms. And the action of G lifts on U, and so we can consider a moment map for this action on U. And then a moment map on V is given by this. So mu of x sigma, where sigma is an element of the Lie algebra, is equal to the integral over U x of tau sigma, and the difference in the scalar curvature minus its average. And plus R is the dimension of P of E, and yes. Where essentially essentially ux over b is the vector bundle given by P of E with the del bar operator induced by the map phi of X. Okay, so this is all from the Darban-Holloman machinery. And so from this, we see that a zero of the moment map, so a zero of this moment map mu that comes from this theorem is equivalent of having that the scalar curvature is minus its average is orthogonal to the Lie algebra K. And so the next on this at this point x, so 0x of mu, and so the next step is to change omega, the relative Kaehler form with so this is omega k. So omega depends on the adiabatic parameter, and so it's to change omega with a Kaehler potential to prove that the scalar curvature function is actually in the Lie algebra K. So that the scalar curvature of this omega k tilde j x is in the Lie algebra K. So that having a zero of the moment map is actually equivalent to having a constant scalar curvature metric. And so once this is in place, then the final step is where the stability condition comes in. So this second step is unobstructed. It doesn't use the stability, and until now I haven't used the stability condition, but then in the third, the final step is where the stability condition comes in, and this uses stability plus, so stability in our sense, so adiabatic slope stability, plus the moment map flow. To produce a zero of the moment map. So the moment map flow is given by, so on B is given by the gradient flow of the norm square of the moment map, or minus maybe. And so if we start the moment map flow from the point that correspond to our original vector bundle, semi-stable vector bundle, then we can find a limit point. So the limit, so you can find a limit point, and stability implies that the limit point is a zero of the moment map, and it actually lives in the orbit, so it's in the same orbit of the starting one. So it's an actual solution on an isomorphic vector bundle. And yeah, so this is because so the stability condition for the flow, for the momentum of flow, is the positivity of the weight that Chauvet introduced in the previous talk, so mu of x infinity with the element of the Lie algebra that brings you to that to x infinity is, well, in my case, negative. And so this is what, yeah, so in our case, this weight is actually the Fourier invariant of the task configuration. So yeah, it's the Donaldson Fourier invariant. Yeah, it's the Fourier invariant of the central fiber of the task configuration. Induced by this element of the Lie algebra. And so this is what was called the Fourier invariant in the previous talk, and in our case it's actually the Fourier invariant. And which we take to be the negative of the Donaldson Fourier invariant as a convention. And so, yeah, maybe in the final few minutes I can write how does one compute this Donaldson Fourier invariant more explicitly. So if we start with so S in P in quotient Q, so if we start from subbundle S that is destabilizing, so mu E equal mu of S, then the formula for the Fourier invariant of the central fiber of this task configuration used by S, well, right, maybe sigma S to be the element in the Lie algebra that induces the task configuration, is equal to the following. So we have n is the dimension of the base, and r plus 1 is the rank of E, and so we have this a very long but also very explicit formula. We have this scalar curvature term, and then we have a term on the subbundle. That involves the Kaehler class of H times the quotient bundle, and then there is another similar term. Which involves the volume. And these are the total Kaehler class. And so this formula is obtained using Evelyn-Legendre's localization formula. And this is useful because it only involves quantities on P of E and on the projectivization of the relevant subbundle. And I guess I can stop here. Thank you.
Great. Questions?
Can you give a simple, concrete example of a vector bundle that is strictly slope-semistable, but also simple? Am I correct in believing that there are no such vector bundles on smooth curves?
Yeah, I think if the base is one-dimensional, maybe you're correct. But we have been working on an example over the blow-up of P2 in a point where there is a rank 2 vector bundle with a rank 3 vector bundle with a rank 2 subbundle that destabilizes it, so that has the same rank, and that's simple. And yeah, admits such an extension, and you can compute this formula in that case, and it is actually, so the Futag invariant is negative, so the Donaldson Futag invariant is actually positive. But it is, yeah, it's not like immediate to produce one. Thank you.
Does this theorem that you have somehow fit into this like a reciprocal theory of like if you're CSCK and you're this holomorphic, then you're also somehow CSCK on the lower?
You mean the whole story or this example?
Or is it just like this statement that you have? So for example, like if you're low up, you're also like in kind of like a projectivization setup, since you're like projectivized the normal bundle. That's then it's not a vector bundle in this case.
Yeah. No, I don't know.
Maybe like those.
Yeah, I haven't thought about that.
Anything else?
So if the bundle is not simple, can you still conclude there that maybe your XCV will not belong to the C? Or?
So if the bundle is not simple, it means that you have automorphisms on P of E. So maybe it might be possible to use a similar technique to produce extremal metrics instead. But yeah, I think the flow part should maybe still work, but I don't know. Yeah.
Anything else? If not, let's thank Annamaria again.